I'm not having to do anything. Okay.
Yeah, it's all the same platform. Okay. So, hi everyone. My name is Sarah Jacob, and I'm part of the Young Professionals Committee with CGS, and I'll be hosting today's webinar. I just wanted to mention a couple of things before we get started. So please make sure that you post all the questions for the Q&A in the Q&A box, as I will not be checking the chat during the course of the webinar. And if you have any questions that we haven't gotten to, or you have questions later, we can get that to our speaker. Coming to today's speaker, today we have John Nichols, who's a geotechnical engineer and excellence and innovation lead for rock engineering at Stantec. John has over 13 years of experience on several geotechnical, rock engineering, and mining projects. His areas of expertise include rock mechanics, rockfall assessment, geotechnical analysis and design, rock mass characterization, rock slope remediation, rock support design and installation, and geotechnical monitoring. He has participated in numerous geotechnical studies in the industrial, transportation, commercial, and residential sectors, and has been involved in both planning and execution of fieldwork, project management, engineering analysis, and reporting. So clearly, John has immense experience in both rock and soil mechanics and is a great engineering professional, and I'm sure today he'll be able to offer us some very valuable insights into the industry. So welcome, John, and I'll pass it on to you.
All right, thanks very much. Welcome, everybody. So the presentation today will be on the basics of rock slope engineering, from understanding the problem to remedial design. I'll discuss the fundamental geological process that create rock masses and the methods used to characterize them for engineering purposes. I'll use an example project. I'll discuss typical rock slope design and remediation, and I'll finish by talking about innovative tools and technologies used in rock slope engineering. So before we get started, I think it's important to do a safety moment. And you can see from this photo taken on a project a few years ago. If you can't see the hazard now, then look a little harder. There's a rope access technician sitting on a spot that's being spot bolted, and essentially he's not paying much attention to what's going on overhead. So we know this is an unstable slope, and we know that it's not it's pretty typical to be next to a bolting pattern like that, but he should be off to the side. He should be focused on the work being performed. So this is a great instance where, as we work in these hazardous areas and rock slopes, we should use our stop work authority. We want to protect not only ourselves, but everyone around us. If we know a hazard exists, we need to say something. So I want to just encourage everybody to, when you see something, point it out, talk to your supervisor, talk to someone else. But I think it's important that we don't let hazardous activities happen on our sites, and we make sure everyone goes home safe. Okay. So my presentation today, I'll do a brief introduction. I'll talk about characterizing rock masses. I'll talk about the processes for rock slope design and the remedial tools we use. Like I said, I'll do a project example, and then I'll do some innovative tools in the future a little bit and how I see stuff working, and then I'll finish by a few questions. Okay, so geotechnical engineering. We typically can divide that into two basic major branches of soil mechanics and rock mechanics. Many of our structures that we work on today, we encounter soil conditions and flat-lying areas. And I would say, from my perspective, it sort of dominates the world of geotechnical engineering. It's weaker, it can be a little more problematic. However, and I think too, it's from my experience, it can be common for and geotechnical engineers focused on soil mechanics to maybe misinterpret rock properties. So I'll give an example, like working on a slope above a soil and the rock is just considered impermeable, solid material. It's not always the case. So, rock slope design is required for a variety of engineering projects, from highways to railways to dams to industrial and residential development. So with that in mind about rock mechanics, it's usually, rock mechanics is confined to the stronger, more lithified end of the spectrum, where the mineral grains are lithified or cemented over geological time. So, by definition, soils have no true cohesion. Therefore, any material that has any true cohesion or tensile strength should be defined as rock rather than soil. So in that case, like rock, and even in that realm, rock can be really broken into weak rock or slash soft rock and hard rock, And like the term weak rock is sort of defined by the International Society of Rock Mechanics, or the ISRM, as something between like 0.25 MPa to 25 MPa. And I've often heard these being called intermediate geomaterials, cemented soils, etc. So for, considering soil and rock, the transition, we'll use like a 1 MPa. So this represents a rock that can be scratched with the thumb, broken into small pieces by hand, but it has tensile strength. So just for reference, if people have done some coring and you take, a typical piece of core at NQ size and you break it, you're able to break it by hand, I would say that's typically about a 12 MPa rock strength. So in comparison, typical concrete is probably 20 to 50, and rock can exceed up to 400, I would say. So, we're talking a very weak, like most people might not even call it a rock. And this photo is an example of one of these sites where we visited, and it was very much a weak rock. And you can see it standing quite vertically. And we often use UCS to characterize rock. It's pretty typical, and we rarely classify it with tensile strength or shear strength. But those are important to our practice. Okay, so we talked about compressive strength of 1 MPa. It's the weakest end of the rock mechanics spectrum, approximately. But it's not insignificant. So if you see on this slide, over here, we have this like typical Mohr circle diagram showing uniaxial compressive strength on a rock sample. You could crumble this by hand, okay? If we actually load this, and this is just an example, there's no real numbers here. So by 1 MPa, we could see that we can estimate a friction angle and a cohesion of about 260 kPa. So I just want to illustrate like a theoretical analysis here to show that even in very, very weak rock, few engineers would even call it a rock, we cut that at 75 degrees, typical cut angle. It can reach heights of about 100 meters and still be stable. And so I use some slide software and rock science to do that. And this is a very basic analysis, but I think it demonstrates the importance, of looking at rock different than soil. This is a weak rock, but it's still quite able to be cut very steep, very high. Now, this is a simplified example with, no water or anything involved. So that would dramatically change how this was looked at. So maybe some engineers would think, oh, that's how rock is. It's just really strong. But, the major flaw in this analysis is that most rock masses, even cemented over consolidated soils or par-cemented soils, contain natural discontinuities or flaws in the rock. And these discontinuities are where rock engineers make their money. They live there, must be considered. So this is the major difference. Rock engineers seek to capture the condition of these natural discontinuities in the rock mass. Okay. So like I said, these discontinuities are natural breaks in the rock. And typically rock masses contain networks of these, and they develop through geological history. These discontinuities control rock mass behavior at a large scale, including strength, deformation, permeability. If we look at it in a holistic view, like discontinuities are very important in the mining world. They're often associated with complex structure where mineralized zones occur. So for engineers working in that field, understanding the mechanical properties and the engineering strength of those discontinuities is key. So like the creation of these discontinuities, stresses are created in the earth by many different methods: plate tectonics, mountain building events, burial, sedimentation, glacial rebound, whatever. And these features help contribute to these breaks in the rock mass. Fractures, the development of fractures is gradual at each stage, and propagation in the rock mass loses strength before it can be fully developed often. Therefore, like rock masses will contain a network of planes of weakness at varying degrees of weakness. So not all these are created equal. It's something that you should take. So you need to understand the weaknesses that are associated with each type and how they should be classified. And not only that, but there can be multiple events in the Earth's process that create these discontinuities. So, and they can be layered on each other and it can be complex. So a detailed structural geology study of the rock mass is very important to understanding these fractures and these features, and from an engineering context. So it's also important to look at the scale effect of these because, it's not everything is impacting your project at the same level. So with intact rock, if you can see from this diagram, depending on what you're looking at, it may be sufficient. If you need to, intact rock governs the intact properties that govern what you need. If you have a single plane, that changes it again. If you have a dense jointed rock mass, that changes it again. So these are very critical to how we look at rock engineering. So there's lots of different types, but we generally try to group them together, okay? And so discontinuities, like I said before, they're weak natural breaks in the rock mass having 0 to low tensile strength. So it's important to group them according to that. I would say a typical error that I see sometimes, and when I look at data, if we use bedding and if bedding is intact and not actually weak or very low tensile strength, it can be lumped in together with bedding that is in fact a discontinuity that has no strength. So we have to be careful when we look at these types of discontinuities that we separate textures, we separate how they're important. I would say, fault, obviously anything with a fractured, faulted material would have more importance than something that, a bedding with more strength. So grouping these together is critical to our understanding of how they'll behave in a rock mass. Okay, so that's a good segue into how we characterize rock masses. So what are the methods we're going to use? What are the features in the rock we're looking? How do we measure it? So like any good field program, it should start with a desktop study. You have to look at what's been done before. You have to dive into the mapping, the structure, historical reports, and you need to create your geological model, which should include rock type, boundary conditions, if there's faults, this is often overlooked, like faulting in the air, even how the existing units are together, if there's intrusion, any weathering or alteration, all sorts of events. And again, setting out a good plan, knowing the potential complexities and difficulties at the site is an important skill for a rock engineer. This photo above here, my colleague and I visited the site, Gabby, and you can see this is a silt lens. And only over time, as that eroded, as the project continued, did it become a problem. It became a concern, but identifying this early, studying it, knowing these exist, it made this project was on pause and these construction delays. So it's only as it progressed at weather that people started to take notice. So we need to understand the site. Even after it's exposed, we need to map it and further understand it. So we need to get in the field. We need to get out there. We need to see stuff. And field mapping is critical. Especially for rock slopes. And it needs to be completed. Understanding these joint sets, their parameters. It's different than a borehole drilling. You don't see the persistence. You don't see the character. You don't see how they interact, how this joint set interacts. So you really need to see it. And sometimes it's not only until it's exposed, it's blasted, that you can really make that assessment. And if you do borehole investigation, you need to confirm the borehole conditions that you see. So, and sometimes if your site does not have, say, for example, any outcrops or any exposure, sometimes it's important to do a trench. You can excavate a trench, you can cut a trench, and maybe worth gathering the data from the discontinuities before you make a deeper excavation. And again, it's important to make sure that you see it, and not just from a pinhole or borehole, but more from a holistic view. So when we get out to the field and we do our field mapping, this is generally what we're trying to find. We're trying to describe the rock type, the strength, the weathering, the discontinuities, the type, the orientation, roughness, aperture, infilling, and then from a rock mass perspective, the spacing and the persistence. These are the key features to mapping, and we need to capture all of them and make sure that they're noted. So how do we do this? This is an example of one of our mapping sheets we use. So we'll go out in the field. But often what we'll have to do is we'll have to break this site into domains. And it's important because domains, they can be like breaks in what constraints are related to the site. So if you have a rock cut or a rock slope and it's below a building with no catchment, or the building's right up against, it's just different constraints and it's different conditions. But with that, it should be noted in your field mapping and understanding it. You need to understand if the slope turns, if it changes, the orientation changes, the height changes, you may intersect a set of discontinuities that you didn't intersect at a different orientation. So, and again, with the spacing of some joint sets or discontinuities, you may not be a problem for this one cut, but it may be a problem for another orientation of a cut or height. And again, another domain you want to break is any geological conditions. And I see this like where there's water running over the site, we're weathering different rock types or different types of discontinuities. These are all conditions that would allow you to sort of make note, break it into domains so that you're not applying the same thing to every location. And often you'll capture different things in different areas. So sometimes you won't capture this detail and can be applied. So you need to make sure. Okay, so that's sort of the way we do it. So now that we're in the field, we're going to do some map. Like this is a great example of some weathering. This first photo over here. It's a highly weathered area of rock mass. This has big implications on the stability, on the properties that will be designed for. The tools used to remediate something that are different than a fresh, other, more competent piece of rock. And these can come in very, narrow bands, or they could be very wide. So definitely need to look at the weathering. Again, the strength, we talked about this before. Key, get out in the field, test it, use your geological hammer, do some index testing, make sure you have a good feel for what you're going to deal with. Maybe the surface is more weathered, but further in it's not as bad. Then we have like your mapping, just your spacing, your persistence, how closely spaced are these joint sets? How long do they go? What kind of problems can I foresee from that perspective? So now we have those conditions. Another very important is like how these surfaces of these discontinuities interact. So we can look at it from a couple different ways. This is my colleague Rebecca here taking a measurement of this long discontinuity. So we can look at it from a waviness. We can look at it from a field scale, first order, and you can apply certain shear strength parameters using those. And then you can apply it to a secondary scale, a lab scale, more centimeter scale approach. And so looking at it from different perspectives, these could all add to how it's used in the remedial design or the solution to your problem. So roughness is one of the key factors we look for. It's very important. And one of the most important, the most critical is the orientation. You can see like we need to understand at what orientation these are dipping and how they can impact our site. This is a photo of me, taking a measurement on a slope using my compass. And I would say that, if anyone who's done any field mapping, the compass is tried and tested, but I wouldn't give it up. It's the good field truthing, and it's very critical to good engineers to have confidence that if you do remote sensing or remote whatever, you still have that compass, that field set, and you're confident in what you've got. So there you go. So I kind of hinted at this, like there's new techniques. This is a new technique to collect the orientation of some of these discontinuity planes. And so this is done with terrestrial photogrammetry. Again, a great tool, depending on the scale of your project, to quickly go capture data. As we advance into more and more different technologies, going back to the tried and tested quick way, and it's oriented nicely, I would say keep it in your toolbox. You never know when it'll be appropriate. So this is a photo of, I think this was almost 10 plus years ago in a mine site. So still a good tool. I used it the other week too. So I would say it's a great way to collect lots of data. And the advantage of using these remote methods is that we're able to say capture that joint set or that discontinuity set that's way up on the slope. We're able to measure the length. We're able to get way more data. We're able to and justify that when we create these sets or these groupings of discontinuities, we have a good understanding of their orientation because the random fractures and breaks can be sorted out. So where it's progressed now is that, and we use drones to collect data. And this is again, making our lives a lot easier. We're able to get up and, collect from much further away. The terrestrial was limited to sort of what you could see, and the data may have been lacking. So field mapping, orientation, data collection with a drone, it allows us to capture much more data. And not only the orientation data for the field mapping, but visually seeing these areas with a drone, if it's like a weathered zone, if it's some faulted feature, you have an image, you're able to get up there with a drone and take a nice picture. I remember going taking helicopter rides to do the same thing as a drone would do. So this technology is really taken off in the future. And if you're into this work, you know that drone work now is LiDAR capable. It's also like it has RTK systems to make it a lot easier. So this is sort of where the future is going for orientation, discontinuity orientation data collection. Now, the borehole drilling, it's still critical. It's still used. And if you have any people who don't do much rock mechanics or rock engineering, you're probably aware of the RQD. That's a pretty basic term, but it's a very great measure of the rock quality from a perspective. We need to make sure when we do borehole drilling that we use good techniques like triple tube. We protect the core. When we do measure it, we're able to distinguish from the natural fractures and then the artificial ones that are created by the excavation, by the drilling process, and the removal of this core from the box. So it's important, and I think that's for anybody collecting rock information, borehole, rock core. That's a distinguish between natural and artificial is key. Not only that, when we're at using borehole investigation, we're able to use, if we're using a televiewer survey, which is a downhole instrument to collect orientation data, we're able to really increase the amount of data we can collect. We can compare that to our orientation data from drone or field mapping. We really have a powerful set of information to compare against each other. And with drilling too, if you don't have any exposed faces for your excavation, you will get some rock quality. You will find out some fracture zones. And even if you can correlate a fractured zone at the surface of an excavation, drilling behind a rock slope will allow you to correlate and maybe give it some more information if it narrows out, if it extends, all good stuff. And again, we'll still get roughness data, shape data from borehole data. You'll notice that this is angled, this borehole. And that's really important when we do studies for rock masses because you can't really do a split spin with an angled thing like this, but what you can get is if you have a vertical or subvertical joint set, you're able to get that with that angle. If you drill vertically downwards, you may miss it because it was just too vertical. So if you're drilling at an angle, you may intercept multiple ones like this, and you'll be able to understand their presence. But not only you should make sure that if you do angled boreholes, that they can be sort of perpendicular to each other, so you get it in every sense. Okay, so there we collected all our data. We're ready to go. So we're going into the design and remediation. So when we look at rock slopes, they can generally be broken into 4 scenarios, we'll say. Weak rock, which we sort of already discussed, intact rock parameters will rule. Rock mass, structural control. We'll talk a little bit about the design approach for rock cuts and rock fall. And then we'll look at some basic remedial measures. So the three scenarios are shown here, illustrated in Wiley 2018. So weak rock, you can see intact, rock parameters apply, but keep in mind that like even if you cut a rock slope in weak rock, weathering degradation in this over time could lead to the change in the intact properties. So then you have structurally controlled, right? This is the second image here. This can often be controlled by a single bedding plane, a single joint set, or two, or however they interact. If you can have this, so the properties of that single joint set are very important to understand, including the roughness, the waviness, any sort of the persistence of it. If it, there may be a rock bridge, the weathering, the strength of the surface, all important things to consider to understand how that slope will be safe, or the planning for that excavation. And then you have your final one, which is the rock mass. This is sort of a hybrid between a single discontinuity and a weak rock mass. So it's looking at how this interaction of multiple, maybe less persistent joints will interact to create, to be how we're going to, the spacing of these discontinuities, the surface condition, how all these interact to provide stability. So again, we went through this already. The weak rock, without adverse or discontinuities, we use like lab testing. We understand, this testing. We understand the properties, and it's generally not that we don't often see this. Like I said earlier, most rock masses in nature have some level of discontinuity, and if it's not a discontinuity, it may be another feature in the rock that impacts it. Maybe it's the actual composition, that there's sandy layers or something like that, the layering of it. So that's important. Now, this is a pretty important one that we often is a big step is maybe these structurally controlled failures. So we can generally break structurally controlled failures into three methods: planar failure, wedge failure, and toppling failure. And you can see that these three scenarios, the orientation of these features was in the perfect position to allow for this to fail. But the good thing is that often if this combination of orientation and persistence and don't line up, then these failures may not be possible. So we study this process to see, how we can deal with this problem. So to do this, obviously we have to start with the mapping. We have to map the orientation and the strength of these continuities. And the next process is to, you can see in this faint red and yellow, I've done some SketchUp of this outcrop. We take that data, and we put it on a stereographic projection. This allows us to find sets of joints or discontinuities, and then we can decide which ones interact with, which ones are random joints, which ones there's enough of the same orientation that this is a consistent set in this rock mass. And then we can, using that data, we can look at, okay, if I cut this rock at this certain angle, at this orientation, how will that impact the stability? So then we do a kinematic analysis. So I'll dive into a bit of the kinematics a bit. So again, this is the stereographic projection, and you can see the kinematic construction lines are all these black ones here. The friction angle here, because it's a sliding plane. If it won't slide unless it overcomes that initial friction on the surface. And then for this scenario, you can see the joint sets are located at certain locations here. The concentrations are the coloring. So we've grouped them and they're labeled as well. So in general, this orientation, there's not a joint set present in this orientation. So this blue is the slope face. There are, however, some joint sets that are present, and you can see just at the edge of this numbered joint set, we just missed this joint set. So ideally, you want to avoid any of your, discontinuity planes intersecting this critical area. But yeah, sometimes you just, you can, and this is where you can play around. You can say, well, can we cut it at a different angle? Can we cut it steeper? Can we change the orientation to avoid any of these potential problems? So how do we move from there? So here's an example of a planar failure. This was a site we visit, and this is clearly an obvious planar failure. This is just showing this kinematic analysis for planar failure. I don't have this isn't the exact stair net for this, but for illustrative purposes, if we knew that this was possible and this was the mechanism failure, we could come up with remedial options, remedial plan to stabilize this block that we knew was sliding. So, and this is a rock plane by the Rock Science software, and this is a typical approach. Now, this is just we can use basic block analysis to come up with the same calculations, or we can use software. But this is the design analysis approach. If we look at a wedge, it's very similar. In this red here, you can see a potential wedge. So we can see that this culmination is worked out to be just on the edge of this red area, which is a potential failure area, or this is the geometry is such that this will slide. And again, we can look at it like that. We can apply this. We can take the two critical, we can actually measure these exact planes, these persistent long planes, and then we can put them in software. We can do an analysis ourselves with hand calculations to determine the friction and what it'll take to overcome and the factor of safety. Another classical kinematic analysis would be the toppling failure. I don't see this too often. It may not be that sometimes the toppling failure isn't as a large scale, and sometimes it results in maybe more rockfall potential as opposed to big scaled rock masses that need intervention. So often, designing these tools that I'm showing you the last couple of slides are really for stabilizing a block. But toppling isn't always the most common we see, but I put it here anyway because it's worth noting. So that's structural control failure and sort of how we approach that. And then we can look at a more of the rock mass. So if we have a rock mass that contains like a network of joints that is complex, and we don't think a single discontinuity is going to control the failure here, this is when we sort of look at the Hook-Brown strength criterion. So, this criteria was developed, it was developed in the 80s. Initially, it used RMR, okay? In 1984, it switched over to GSI and became the generalized Hook-Brown. We use certain parameters, and this is the accepted method to come up with the more Coulomb friction angle and cohesion of this rock mass, and how we can cut it at certain angles and certain heights for it to be stable. So using this chart on the right, you can see we look at the discontinuity spacing, right? Whether it's the structure, more appropriate, like the blockiness of it, compared to the surface condition of those joints. And using that experience, we can come up with, say, a GSI number. It should be a range. You should never be very precise with it because it is, and this is a very, the more practice you have at it, the more rock slopes you see, the better and more calibrated you'll get yourself. Keep in mind, this is for, isotropic rock masses only. If you have planes of weakness, like the structural, you may want to use other methods to complement this, but this is the generally accepted method. And these are, some of you'll have to give it some constants, the intact material constant, disturbance factor, how fractured it is. You'll also have to look at, the unit weight of the rock and the height of the excavation, because the stresses in that are important. So, oh yeah, here we go. This is rockfall. Okay, so this is the more typical approach. I would say rockfall is sort of a combination of weathering, but also like how we how these play out. And you often see in media like this will be thing that brings you to the site is a rockfall event. And this is an example on a roadway, and this is an example on someone's patio. So, these small failures, not necessarily controlled by a major structure, but just general erosion over time. It could be multiple factors, a heavy rainfall event, anything like that can lead to a rockfall. How we deal with rockfall is a little bit different. We sort of look at it from, okay, if we know this source rock or these fractured blocks are present, we sort of, if we're going to design for these and analyze how they impact the site, we sort of have to just roll them down the hill. So we use 2D or 3D models, and we pick certain block sizes, certain densities, and and then the surface parameters that we apply to the rock surface will dictate, once they impact the rock surface, what energy will be transferred to the next bounce. So we look at it from that perspective, and we run these tests thousands of times. We can see where it typically rolls out. We can change the shape. We can change, the initial velocity, stuff like that. So this approach is how we look at rockfall. Okay, so we know the problem. We know we got to do something. What do we do? So I would say the choice of remediation or remedial design will be different for each project, and the consequences of failure. That's so important, because you can see, like, if we different areas may not require the same approach, but if you risk or the consequences of a rockfall are high, whether it's a busy road or apartment building or housing, it really raises it. Whereas if it's a rock fall or a structural failure that's relatively in the middle of nowhere, no one really cares. So the options are, based on that, we can do nothing. We can just let rock fall or failure occur. We can do non-engineering options. We can say, look, these are certain things we think are appropriate, administrative controls, and then we can do the engineering options. We can protect ourselves from rockfall or sliding or failure. We can stabilize, right? We can stabilize by two different means. We can remove the hazard, or we can reinforce the slope. So I'll get into a bit of those. So, like I said earlier, maybe the hazard is present and we just don't think the consequence is that important, or maybe there's just not enough, maybe for budget reasons, but we're going to use non-engineering measures to solve this problem. So typical warning signs. You can see in this photo, how many of you have driven on the highway and seen one of those signs and thought, what the hell does that mean? So this is, we're warning us, we got to protect ourselves. We can restrict entry to certain areas. We can make monitoring programs. We can clean out ditches on highways or roads, and we can do road patrols. So these are all sorts of stuff we can do to protect ourselves from rockfall or hazards from rock slopes. So if we decide to go ahead that the risk is too high, we need to stop the rock, whether it's for a foundation above the slope or if it's properties below. We can choose two different methods. We can stabilize the slope with reinforcement. This is your standard rock bolts, shotcreting, buttressing, even drainage is good. Or we can remove the hazard. And that's the preferred option for most people, is to get rid of it, because everything that you put in the slope will degrade with time. Piece of steel, anything. So we need to keep that in mind, that there's design lives associated with these reinforcement, whereas it's less with the removal. The other approach, which is very, very common, is protection. And this would be like ditches. So most highways would have ditches above rock cuts, and those ditches are specifically designed for the height, the slope, and they should catch most of the rockfall that goes in there. If we don't think that that ditch is adequate, we can have meshing over that. We can make fences. We can have rock sheds. That's the most extreme version. You may have seen these some places. They just build a roof over the road at some places to protect themselves. So lots of options available. So we had to choose the right one, the appropriate measure for the budget, for the risk, for all these things. So this is just some, illustrations of what we just talked about. Resloping weak rock, removing overhangs. Removing trees and vegetation is critical as well. And scaling debris is sort of an annual or every couple of years, 2 to 3 years is typical. And again, if that removing the hazard is not required, we can go ahead and we can stabilize it with buttressing. We can prevent erosion using shotcrete, We can put anchors in the slope to prevent it from blocks from sliding. So again, lots of good techniques. We can choose what we need, and it will depend on what site we're working on. All right, so I'm going to go through a project example now. So this site, this is one of my favorite projects I ever worked on. It was in Hamilton, city of Hamilton in Bermuda. So this was a rock slope. And, if you could see from this photo, there was a rockfall event and it landed right on the sidewalk. There's really no catchment here. So whoever designed this, and you can appreciate it's a very steep, narrow cut in the rock, with a bridge in the middle. So, but it's a very, very popular road for these connecting these two busy areas, the beach and a very popular capital city. So this was a roadway with no sidewalks. It got up to 24 meters in height, and had no catchment. And the remedial plan that we did was we did scaling, we did spot bolting, and we did shotcrete. So this is where it's located, just right out in the middle of nowhere. And this dot, you can see this is where the actual site was. And this is really the capital city is densely populated here. So it's a very popular route between those things. So you can see the first thing we sort of did, and you can see sort of in this photo, was the tree removal. It's important because these roots that grow in these cracks over time, there's a weather, and then you get some wind. This forces on those trees and root jacking, we call it, can really cause rockfall to occur. In northern climates, you get frost jacking, which is where water gets in it, and you'll see rockfalls generally occur in areas when as it starts to frost and get hot and cold, and this ice expands in these cracks, but that's not the case here. So removal of the trees, and then what we did is we did a light scale to remove any hazards, because you have you know, appreciate there's a lot of these erosional features in this really weak rock mass that cause it to just over time, it's sort of a differential erosion and they fall off. So these are located throughout the area. But not only that, we do see some of these bigger blocks that were sitting on these like dipping bedding planes in this limestone. And it didn't take much to give these a push, and they came down. And you can see this not a very strong rock. It really breaks up pretty quickly, but it still contains these discontinuities that control some of the sliding. So what do? We did some, after the scaling, we bolted some of these blocks that were at the crest, the most hazardous ones that were also impacted by, some of the erosions falling from the higher. They needed to be bolted in to make sure that they didn't cause us any issues. So you can see here installation of some rock bolts and yeah, grouting them in place. And they were passive. They were fully grouted dowels acting as support there. Next, we had sort of this big erosional feature that was clearly undermining the entire slope. And it was over time, it was getting worse, and this is what the client was telling us. So the real solution there was to ensure that we protected that weaker area with some shotcrete, protected it from further erosion, but also gave it some support for up above. But we knew that it had lots of water and drainage in the rainy seasons here, and that's what's causing this to erode, the way the water goes through the slope. So we had to come up with these drainage throughout the site and some pinning. So that's essentially what we did. We came up with a rock bolting pattern and some drain holes and the extents of some shotcreting. And yeah, so this is sort of the design. We had filling it with some dental concrete in these voids here. And then we had a welded wire mesh anchored to the slope and applying shotcrete. This was the first time shotcrete's been used on the island, and I think it was a great alternative to some of those. You might have seen those cylinder block walls that were present. They can be problematic. We actually removed quite a few of those during scaling. They actually became a hazard. So, all right. So finally, I just talked about a few innovative tools. I mean, I already mentioned this earlier, but like the drone, I got the first drone we ever, got was in a couple of years ago, and it really changed the way we collect data. But now I know that the data collection is changed even again. Now we can do LiDAR data. We have these RTK drones, and it was just going to really make that data collection easier and faster and more reliable. Um, and I will say, not with the drones as well, using these as sort of a monitoring tool. Sometimes we like to see how the slope changes year after year. If we can quickly perform LiDAR surveys with drone, we can probably better understand sort of how the slope behaves. I will say, innovations in situ testing, the availability of these downhole televiewers combined with other services, dilatometers and stuff, it's really becoming a much easier tool to operate and cost effective. And with all that, integrating these into the software, some of these new softwares allow you to collect straight from your drone to your structural kinematic analysis or stereographic projection, and then right into your analysis software. That's great, but I'd also encourage that, nothing beats, you getting back to field truthing, looking at stuff yourself, because we don't want to let data overshadow some stuff. But these are great tools, and they're really pushing the envelope in rock engineering and slope stability, rock slope engineering. And finally, I would like to innovation sometimes can be daunting if you look at it from, oh yeah, that's just software related or tool related. But I think innovation can be in the field. And this center photo, Stantec has done a lot of talking about this, but it's this removable barrier that we worked on a project a few years ago. And the idea here is that you found an innovative solution to protect the workers working in this rock cut. They needed their demands, we knew there was hazards, so we came up with a solution. And these other two photos are examples of a similar approach. We see hazards, we try to minimize the safety to the rope access people, and also everybody working on the site, so that when we walk away, we know that the hazard was protected for the end user, but also the people working on the slope. So I think that's important in rock slope engineering. So that's my presentation. I think I'm at time. Thanks for everything, and let me know if you have any questions.
Thank you, John. That was great. We had some very valuable insights about practical rock slope engineering. And I encourage everyone to post your questions in the Q&A box, please. We have one question in. How often are tensioned rock anchors used? Or maybe under what conditions are they generally used?
Yeah. So tension rock anchors, or active anchors, typically we use those if we want to pull, if we know we have a defined structure or a defined discontinuity, and we think there's value in pulling that discontinuity closer together. Because I will say, when you pull that discontinuity together by tensioning the bolt and applying friction, you increase the strength of that rock mass much better than if you had a dowel. When you put tension on a rock bolt, you increase the friction and sort of the apparent cohesion of that surface. And you would do that if you had, say, a defined surface that you wanted to protect. A passive bolt could be used to that effect, although it's going to be more, it's going to be reaction. It's going to, movement of the block is going to engage it, as opposed to an active bolt that's going to keep it close to the face.
Great. Thank you. I see that some of your hands are up. If you could post the questions in the Q&A box, that would be great. I have another one. It's a bit long, so bear with me. What would your approach be to assess the stability of a large cutting in fleece material, such as tectonically deformed clayey shales? Would it be based on kinematics, Hook-Brown criteria, or a combination of both? What are some design solutions for cuttings in these materials?
Yeah, okay. So I kind of hinted at that. So that'd be an anisotropic material, not an isotropic material, right? A shaly, is this, if my understanding correctly, like a shale. So first I would do is I would see, kinematically, if you have daylighting. And daylighting would simply mean is the the dominant in shales would be that schistosity, right? Or the so if you the shaliness of it, if that is dipping out and daylighting, or then you would look at the strength of the actual plane itself, which is relatively weak in a shale. Shale is typically a very weak rock, but then I would probably apply also anisotropic conditions to that slope. So I would look at it from kind of like the rock mass, but I wouldn't, the parameters I would assign it would be there's a couple methods you can use in design software, but these anisotropic methods, like the Snowden method is one very popular one we use. So it's basically saying, okay, there's when you're not in line with the discontinuity, then rock mass conditions apply. But as soon as that failure surface comes into an area of that discontinuity, then you can apply the strength parameters based on the discontinuity strength. But again, then shale would be a good one, because sometimes you look at it, if it's a very weak material, maybe if none of those, if it's not dipping out of the face, maybe it's an intact rock strength parameter. So I would start with the orientation, and then I'd start with understanding the intact rock strength. Yeah.
Great, thanks. Another one, can you elaborate more on the difference between rock bolts and anchors, passive rods versus hollow bar anchors? Sorry.
Okay.
Yeah.
So yeah, passive, like I said, passive bolts are not tension. They're relying on sort of a fully grouted dowel to engage. And sometimes it's acts in shear as well. Like if you take the strength of the steel bar and you apply shear strength to that bar, um, it sort of it reacts to movement. It doesn't prevent movement, which depending on the orientation and the application, passive bolts are much easier to install. When you do an active bolt, you need to make sure that you're behind the failure plane, and then you tension it, and then you can finish your grouting. A hollow core and that was mentioned, those those would be used in a passive bolt scenario. Those would be when very poor rock quality is present, and you essentially do not think that you can pull out your drill, when you do downhole hammer to open the hole, you think that the quality is too bad, and when you pull out, you won't be able to get your rod in. So in that scenario, we put a drilling head, a drilling bit at the edge of our, our anchor, and we drill it to depth, and we grout it from inside. So hollow core is very expensive to use and has a specific application for poor quality rock. Yeah.
Okay, thanks, John. The next one, what are some features you look for to know if a fracture is natural or caused by drilling?
Yes. So often my first reflex is if it fits together perfectly right out of the thing, and you can't really see anything, then it's probably mechanical. Um, and so you can often see rough, kind of unnatural surfaces in that break often would be artificial as well. You can often, and another feature to an artificial break that I didn't really get into is this feature called disking. So if there's stresses locked in the rock mass and you de-stress it, the rock may disc. And that's sort of another artificial feature of the rock mass that you'll see. But more to your point, an artificial break will fit together really well. It would also be very clean and fresh for the most part. So those are two features I would look at. Having said that, if I wasn't sure if it was artificial or natural, I would be conservative and I would consider it to be a natural joint in my analysis.
Yeah, great. What programs do you use for drone photogrammetry?
So we use a software called ShapeMetrics. So it's actually was recently bought by Rock Science. It's an Austrian-based company. They provide, they've been doing it for a long time. There's another competitor out there, Atom Tech, I believe. But I take, using ShapeMetrics, and 3GMS is the parent company, I believe. Um, they the integration with the Rock Science suite of software is really great. And we're starting to see integrations with stereographic projection software dips as well, and other things. So yeah, shape metrics is what we use at Stantec.
Great. Okay, one more. May I know what is the design shotcrete strength requirement and energy absorption rate for the shotcrete applied in Blackwatch Pass?
I think the design strength, it's about, I mean, compressive strength of the shotcrete, I think is up near 50 or 60 MPa. I will say that like the testing for shotcrete and testing coring. So the process to shoot shotcrete, you shoot a test panel and you core that test panel and you test each batch you do. But one thing about shotcrete, if you've never used it, you need a very skilled nozzle person to do it, and it's complicated to apply to get behind a welded wire mesh. So I think the strength was 50 MPa. What was the other second part of that question?
Energy absorption rate for
I'm
the
not sure about that.
shotcrete.
I'd have to look that up.
All right, so we may have time for one more question if somebody wanted to ask anything. Or maybe I'll end with one of mine. Have you, since you've worked on so many different types of projects, was wondering if you have observed any sort of differences in rock characteristics, or are there any pointers to look for rock characteristics specific to tropical weathering, or something that we observe more in a region like Canada? Is there something that you specifically look for?
Yeah, so like weathering, alteration. I mean, so one of those first slides I showed was in Grenada, down in the south, a little south, just above South America. And I will say that the weathering features there and the rock mass itself, it's such a young rock. I think when you look at different rocks in different areas, like, I can often break my experience into the Rockies, the Appalachians, and then the Canadian Shield. I kind of can tell where I'm at, the rock strength, the rock properties, discontinuity stuff. And then you have in Canada, especially along the eastern, the St. Lawrence sediments, they all sort of have their own grouping, and you can sort of understand where they're coming from. And the weathering associated with those is different. Um, you know, but again, the tropical weathering, yeah, you can see it's a younger rock. It reacts different than an older, more older rock. So
Yeah, that's right. Okay, one last one to end our session. You mentioned the use of split spoon during exploration. Can split spoon be used during rock exploration?
I think I think when I said Switzerland, I said when you have an oriented core, like if you do an angled borehole, you can't do a split spoon because it doesn't really work. But I would typically not. No, I mean, split spoon is a soil parameter. If you're able to split spoon, you can certainly collect. Typically, it gets refusal in rock. Typically, the only method we use for coring is through using diamond drilling. Um, Having said that, if you collect the split spoon and it's cemented soil in a split spoon, you may want to consider rock properties. But no, we don't use split spoons in rock exploration.
Great, and I think we're almost at time. Yeah, there's no more questions. Yeah, so thanks, John. Thank you for your time and for your presentation. It was great. And I think we can end our session here. Thank you, everyone, for joining today. And I hope you have a great rest of your day. Thanks.
Thank you.